Hi, I'm Jenny Kaufmann, and I will be talking about approximation algorithms for min-distance problems in DAGs. My co-author is Mina Dalirrooyfard. So first, what are min-distance problems? Well, the min-distance between two vertices u and v in a graph is the minimum of the distance from u to v or from v to u. You might care about this, for example, if you have a doctor and a patient, and you don't care who goes to see who as long as they do it as fast as possible. Unlike the standard notion of distance, where you could have duv doesn't equal dvu, the min distance between two vertices is always symmetric because it's a minimum. This is a particularly natural notion of distance in DAGs, where if you have a path from u to v, then you can't also have a path from v to u because that would create a cycle. So the min distance between two vertices in a DAG is basically just the distance between them in whichever direction it makes sense to take that. So as with the standard notion of distance, you can define various parameters related to min distance. And the ones we'll be interested in this talk are the min diameter, which is the maximum min distance between any two vertices in the graph. The min eccentricities of the vertices. So for vertex v, this is the maximum min distance between v and any other vertex in the graph. And the min radius, which is just the smallest min eccentricity. So in this example graph here, the min radius is going to be 2, and that's because this red vertex has a min eccentricity of 2. You can get from the red vertex to any other vertex in the graph within min distance 2. All of these parameters can be computed in tilde O of mn time in a graph with m edges and n vertices by computing all pair shortest paths. So I should mention the tilde hides polylogarithmic factors. So all pair shortest paths is basically what it sounds like. It's just computing the min distances, or rather the distances, between every pair of vertices in the graph. So you might think, okay, well, this is a little bit overkill. These parameters don't clearly, necessarily require you to compute all of the distances, just some of the distances. So maybe they can be computed faster, or more realistically, maybe they can be approximated faster. So our guiding question is, in DAGs, within what approximation factors can you find the min diameter, min radius, and min eccentricities in time that is sort of meaningfully better, polynomially better than the standard APSP runtime? Or in sparse DAGs specifically, this would be subquadratic runtime if m is order of n. That is, if the graph is sparse. So to find upper bounds on these achievable approximation factors, what you do is you just design fast approximation algorithms. And our approximation algorithms use techniques like using a lot of graph searches, like BFS and Dijkstra, and also using graph distance applications of matrix multiplication. For lower bounds, well, finding lower bounds is hard in fine-grained complexity. So to make things a little more practical, we use conditional lower bounds, which is very common in fine-grained complexity. We reduce from problems that are thought to be hard in some sense. And the specific problems that we're interested in for these lower bound reductions are the orthogonal vectors problem, the triangle detection problem, and another popular one, which I'll mention here, is the hitting set existence problem, which is similar to the orthogonal vectors problem, but we will not be discussing that because we didn't use it in our paper. But the other two problems I will tell you about now because they're the bases for our conditional lower bounds. So you'll know what those are based on. So the orthogonal vectors problem is basically about, okay, so you have two sets of vectors, and you want to know if there's a pair of vectors that are orthogonal to each other. In other words, a pair of vectors whose dot product is 0. This is solvable by brute force because you can just take the dot product of every single pair of vectors. But you might want to know if you can do it faster. And the conjecture is that you probably can't. You probably can't get better than that runtime by at least by a factor of n to the epsilon. And this OV conjecture is actually implied by Seth, the strong exponential time hypothesis, which is a popular conjecture about the runtime complexity of satisfiability. So if you believe Seth, then you also believe the orthogonal vectors conjecture. And if you don't believe Seth, you might still believe the orthogonal vectors conjecture. You can also consider a variant on the OV problem in which the vectors have a number of bits that is linear in the size of the sets, that is linear in n. In the standard OV, it's logarithmic. So this is called high dimensional OV. And this can be solved in matrix multiplication time using Boolean matrix multiplication. And it is conjectured to require essentially matrix multiplication time. The other problem that we base a lower bound on is triangle detection, which is pretty much what it sounds like. You have a tripartite graph, you have 3 vertex sets, and you want to know if there's a triple of vertices that have a triangle between them. So certainly this is solvable by brute force in cubic time. You can also solve it in matrix multiplication time, essentially by multiplying 3 copies of the adjacency matrix and then kind of looking at the diagonal of the resulting matrix. And it's also conjectured to require essentially matrix multiplication time. Okay, so those are our bases for our lower bounds and our results. So I'll start by talking about our min diameter results. So previously, what was known about what you could do faster than the standard APSP time was that it was known you could get a 2 approximation for min diameter and DAGs in time linear in the number of edges. And it was also known that conditional on Seth, or really conditional on the OV conjecture, you need essentially the standard APSP time in order to do better than a 3/2 approximation. So what we did was we improved these bounds for denser DAGs. So our upper bound, we found a 3/2 approximation algorithm with this funky looking runtime in unweighted DAGs. This runtime is faster than the standard APSP algorithm if m, your number of edges, is superlinear in n, so like n to the 1 plus epsilon kind of thing. And this holds only in unweighted DAGs, and the reason for that is that our algorithm relies on this fast sparse matrix multiplication technique in order to find set intersections, in order to find neighborhood intersections, essentially. And you're doing this in order to find sort of halfway points between different vertices in your graph. But in weighted graphs, you won't necessarily have these sort of halfway point vertices between whatever 2 vertices you're looking for a path between. So that's why it's just for unweighted. And we also found a conditional lower bound, which is conditioned on high dimensional OV, which says that you essentially need matrix multiplication time to do better than a 3/2 approximation. So this is conditionally tight for dense DAGs, and you can see that here in this chart. We have this 3/2 upper bound that we know you can do in this runtime here, which you get by substituting in m is order of n squared, so dense graphs. And this lower bound says that you conditionally need matrix multiplication time in order to do better than 3/2, and this is 2.373, so this is larger than this runtime that we found for the current value of omega anyway. Okay, so what about min radius and min eccentricities? So these are sort of very heavily connected problems, which is why I discussed them together. And previously, it was known that you could get a 3 approximation for min radius in DAGs in tilde O of m root n time. And the lower bound was essentially 2 for better than standard APSP time. And this was conditioned on the hitting set existence conjecture. And for min eccentricities, you can get 3 plus delta in faster than essentially the standard APSP time. And this bound actually is not just for DAGs, it's for general directed graphs. So what we did was we found a 2 approximation for min radius in faster than the standard APSP time. And in fact, we didn't just find a 2 approximation, we found a k approximation for every integer k greater than or equal to 2. So we have this kind of funny looking runtime here. And what's actually going on is that this is 2 different analyses of the runtime of our algorithm. One of the analyses gives a runtime that is better in sparser graphs, and the other analysis gives a runtime that is better in denser graphs. So you just take the minimum to get the better one. For min eccentricities, we essentially had a very similar result. You just add delta to your approximation factor and divide your runtime by delta. And our lower bound for min radius, specifically for dense DAGs, this is useful for dense DAGs, is that you essentially need matrix multiplication time conditioned on triangle detection needing matrix multiplication time in order to get an approximation factor smaller than 2. Which means that our min radius algorithm and our min eccentricities algorithm are essentially conditionally tight for k equals 2 for both sparse and dense DAGs. So here's a chart that kind of summarizes all of that. So here's our tight min radius result, and then lower bounds for min radius are also lower bounds for min eccentricities, because min radius is sort of pretty much strictly easier. And you can see why this is tight in dense DAGs, because here we have this m to the 2/3, and if you substitute m is order of n squared, you get n to the 7/3, so that's the runtime in dense DAGs. And you can compare that with this lower bound, which for the current value of omega is larger than that. So essentially, you can't do better than this 2, conditioned on what we think the runtime is for high dimensional OV and for the current value of omega. Okay, so I'd like to give you a quick overview of what our min eccentricities algorithm looks like. So that will be next. Okay, so this here is basically just restating what our results are. We can 2 plus delta approximate. So this is for the case k equals 2, because that's simpler and it's also kind of the most interesting case. We can 2 plus delta approximate all min eccentricities in this runtime, minimum tilde O of minimum of m root n over delta and to the 2/3 n over delta. And it's basically the same algorithm that you use for min radius, except for these, additional deltas. And the way this is going to work is that we fix some r. And r is basically our guess for what the min eccentricities are going to be. And we check for each vertex if that r is sort of about right, if it's within a factor of 2 of being right in some sense. So we're going to figure out if for each v, if the eccentricity of v is less than or equal to 2r, or if it's larger than r. And then what you do is you test lots and lots of values of r in order to figure out narrow down what exactly your min eccentricities are. And the reason why you have this delta for min eccentricities, but you don't have the delta for min radius, is because there's sort of a lot more min eccentricities than there's only one min radius. So you kind of have to test more values of R, and that's where the delta ends up coming in order to approximate min eccentricities, whereas you can just kind of binary search to get the min radius. So our algorithm will start, well, the part of the algorithm that is just checking for each vertex whether its min eccentricity is less than or equal to 2R or greater than R. It starts by partitioning the graph. So we have a topologically ordered DAG, and we're partitioning the graph into root n topologically consecutive sets. Now what we do is we compute the minimum distance between each set and all vertices in the graph. So when I say we're computing this minimum distance between a set and a vertex, I mean the smallest min distance between any vertex in the set with this V. So just whoever's closest to V, that's the min distance that you care about. So if the min distance between one of these sets and some vertex is large, well, then every vertex in the set has large min eccentricity, because otherwise you could just go from that vertex to get to this V. So then we're kind of happy because all of these vertices in our set have large min eccentricity, so we're done with them. We know what's going on with them. We're good. However, if this is not the case, then we have to actually figure out on an individual basis whether the vertices in WI have large or small min eccentricities. So the way we start is we compute the sort of local min distances within WI by running APSP within WI. And the set is pretty small, so you can do this. It doesn't take too long. And so now we know these local distances, but we still need to know about the distances from vertices in WI to vertices outside WI. So if a vertex in WI is not close to all of the vertices in WI, well, then we immediately have that its min eccentricity is large, so we can just report that. And if it is close to everybody in its set, then we can combine these local paths from it to vertices in its set with paths from these special jumping off sets, which give these sort of external paths. So this is what this is going to look like. If W is our vertex within WI that we want to figure out whether it has large or small min eccentricity, well, it's close to everything in these jumping off sets. So it's within min distance R of everyone in the jumping off sets. And the jumping off sets are constructed in such a way that for every vertex in the outside of this set, there's someone in the jumping off set that's close to it. So that gives you this min eccentricity of 2R, because W can get to the jumping off set in distance R, and then from there in another distance R, so you get a path length of 2R to anywhere in the graph. And the way you find these jumping offsets ends up being this kind of neat technique that involves doing a lot of binary search and running Dijkstra's algorithm repeatedly. So in summary, the way our min eccentricity approximation algorithm works is that we run APSP within these partitioned sets to find the local paths. We use this binary search technique to find these jumping off sets that give us sort of external paths. And then we combine the short local paths with the short external paths from the jumping off sets to get approximately short paths to anywhere. And that gives us the min eccentricities that are less than or equal to 2R. And then you want to test lots of values of R to actually narrow down what the min radius and the min eccentricities all are. So these are the runtimes for the case k equals 2, which is the case we've been discussing. And you can actually improve these runtimes for the specific case of DAGs with small integer edge weights. And the way you do it is you, instead of using the standard APSP, for these DAGs, you can use a special matrix multiplication-based APSP algorithm designed by Zwick, And so for example, for DAGs where the edge weights are constant and they're integers, you get this runtime here, which has this m to the 0.605, which you can compare with this m to the 2/3. So it's a slight improvement. Okay. So in conclusion, what we did was in DAGs, we have conditionally tight bounds for fast approximations for min radius and min eccentricities in both sparse DAGs and dense DAGs. For min diameter, we have something that's conditionally tight for dense unweighted DAGs. So it'd be interesting to be able to close this gap for DAGs that are sparse or weighted for min diameter. And also, what about general graphs? So this has also been studied, and we still have gaps between the upper bounds and the conditional lower bounds for all of these problems. So it would be really cool if we could develop algorithms, or someone could develop algorithms for these problems that got fast 2 approximations. Well, that's my personal guess, is that you can lower the upper bounds to 2. That's going to be what the correct answer is. All right. Thank you so much.